This video is on thermochemistry. Thermochemistry is the study of energy in chemical reactions. When we think of energy, two words usually come to mind: temperature and heat. They're actually two different things. Temperature is a measure of motion or kinetic energy of the particles in a substance, whereas heat, which we can show as Q, and it's lowercase, is a transfer of energy between objects due to a temperature difference. Heat flows spontaneously from warmer objects to cooler ones. So that's why if you were to hold an ice cube in your hand, it would melt, because the warmth, the heat from your hand, flows into the cold ice cube and increases the kinetic energy of the molecules, so they move faster, so then they spread apart and then they melt. When we look at thermochemistry and we look at heat and its directions, we have something called the universe, which is what we look at. In our universe, we can divide into two parts. We have the part of the system and the surroundings. The system is what we're looking at, our reactants and products, and the surroundings is everything else, such as the reaction vessel or the water that surrounds the reaction. So if this is the universe, and I have my cylinder here would be my system, and my surroundings, the area around my system, are my surroundings. If my heat goes from my system to my surroundings, that is a negative Q, which is exothermic. If heat goes from my surroundings to my system, that's a positive Q, which is endothermic. If I were to measure the temperature of my surroundings, so if I were to put in a thermometer, if my surroundings increase in energy, they increase in the temperature that I measure, that means that my reaction is exothermic. However, if my surroundings decrease in temperature, that means that my reaction took in that temperature from the surroundings, and my reaction is endothermic. Let's look at an example of burning methane. So when methane burns, CH4, it burns in the presence of oxygen and creates carbon dioxide and water, a standard combustion reaction. When this burns, energy is given off in the form of heat. Because energy is given off, we call this an exothermic reaction, where energy flows from the system to the surroundings, giving us that negative Q. This energy comes from the chemical bonds. Of your reactants. So between my products and my reactants, the potential energy is less in my products than it is in my reactants. So more energy was broken when my atoms and their bonds shuffled around to make my products, and the extra energy was given off as heat. So potential energy in chemical bonds is converted to thermal energy via heat. It's important to remember that the energy lost by the system is equal to the energy gained by the surroundings. We can make a potential energy energy diagram of our reaction. So still the same reaction before of burning methane. I have potential energy on my y-axis, the reaction progress on my x-axis. That means that I start with here my reaction. The starting things are my reactants, which is my CH4 and my oxygen. It requires an activation energy, okay, so energy to get the reaction started. And then after they mix up and come together and they make their products, my products are sitting at a lower energy, my CO2, my H2O are sitting at a lower energy than my reactants. So my energy of my products is less than the energy of my reactants. Therefore, my energy left as heat, which I saw up here in my reaction. So the change in where my reactants start and the top of my potential energy diagram is called my activation energy. So the energy required to make the reaction go. The difference between where my reactants start and my products end, this is the energy of my reaction. So like I said before, my reactants have a higher energy than my products. It is going to be an exothermic reaction. Let's look at another example, except this time of an endothermic reaction. Given the reaction of nitrogen and oxygen and heat energy, I can make nitrogen monoxide gas. Here my energy is a reactant, therefore it's endothermic. My energy flows from my surroundings to the system, resulting in a positive Q. My energy comes from the surroundings, so that's where I had my container, my reaction vessel, and my energy comes from my surroundings into my system. So energy is being added. This means that the potential energy of my products is greater than the potential energy of my reactants because I needed to add an energy to get to their potential energy. So looking here again at another potential energy diagram, I can see that my reaction progress, which is my reactants that I start with, my N2 and my O2, require in energy, get to their activated complex. So at the top we have an activated complex. So extremely high energy state of my atoms bonded together. And then it comes back down to the products, which in our case is my nitrogen monoxide gas. My products are at a higher energy state than my reactants, so it required heat energy for this to occur. The difference in energy between the top of my graph, my activated complex, and where I started, this is my activation energy. And the distance between where my products end and my reactant started is my energy of my reaction. Notice that this is a positive value. Here we have the required heat. Of my products. Energy can be expressed in different units. The calorie is created off of the amount of energy needed to raise the temperature of 1 gram of water, 1 degree Celsius. So we like to use water a lot in chemistry as our standard. And when we make units off of water, they get specific names. And so in this case, that calorie with the capital C is based off of 1 gram of water, increasing its temperature 1 degree Celsius. It takes 1 calorie of energy to do that. Other energy units are called joules, and this is the standard unit of energy, the one that we're going to use a lot in this class. And joules, just like any other metric unit, you can have kilojoules. So we can have a kilojoule, which is the same as 1,000 joules. The relationship between a calorie and a joule is 1 calorie is equal to 4.184 joules. And a joule, being energy, has units. So if you were to look at the units within the joule, so what we write as J really symbolizes 1 kilogram times meter squared per second squared. So this comes from the fact that energy is equal to force times distance. And I know that force is equal to mass times acceleration. And I know that acceleration is measured in meters per second squared. So my distance is my first meters on the top, this guy. My mass is my kilograms. My acceleration is my other meters, so this gives me my squared here, and then divided by second squared there. So again, this is how joules are a unit of energy. Now we're never going to write the kilograms meters squared per second squared, but it's good to know where this unit, the J, comes from. We also say these units in nutrition. It's what's written on nutrition labels. And in nutrition, we see the word calorie with a capital C. And the relationship here is 1 big C calorie is really 1 kilocalorie, which is 1,000 little calories. We can also talk about enthalpy. Enthalpy is the energy of a substance due to the motion of its particles. So just like heat, it cannot be measured directly, but it can be measured by a change in enthalpy. So delta H, or enthalpy, is the heat lost or absorbed by a system under constant pressure in a chemical reaction. We call delta H Q if we're at a constant pressure. So for a chemical reaction, the delta H, or the change in enthalpy, is equal to the enthalpy of the products minus the enthalpy of the reactants, or the change in enthalpy, right? We can measure its change. If the enthalpy of the products is greater than the enthalpy of reactions, then the change in enthalpy will be positive and the reaction will be endothermic. If, however, the change or the enthalpy of the products is less than the enthalpy of the reactants, then your change in enthalpy will be negative and the resulting reaction will be exothermic. So using the information about enthalpy, we can use something called calorimetry, which is the science of measuring heat, which is based on observations of the temperature changes when a body or species or reaction or the surroundings or the system absorbs or discharges heat energy. So when we look at calorimetry, we must know a substance's heat capacity, which we call capital C, and heat capacity is the heat absorbed divided by the increase in temperature, or joules per degree Celsius. This is how easily a substance changes or increases its temperature. So how easily I can heat up water, or how easily I can cool down a metal. we can have two different types of heat capacity. We have molar heat capacity, which is the heat capacity per mole, or joules per mole degree Celsius. The energy required, so the joules required to raise 1 mole of substance, 1 degree Celsius. We also have specific heat capacity. This is what you've seen before in chemistry, where we have joules per gram degree Celsius, which is the energy required to raise 1 gram of a substance 1 degree Celsius. So the difference here is how we're measuring our quantity of our substance. We can calculate the change in enthalpy of a reaction, and this is the delta H is equal to mass times specific heat times the change in temperature. Change in temperature needs to be in degrees Celsius because of our units on specific heat. Mass needs to be in grams, again, because of our units on specific heat. So we're going to remember back that if two reactants are at the same temperature and they're mixed, so that's in our reaction vessel, and the resulting solution goes up in temperature, the reaction taking place is exothermic, so it's giving off heat. An endothermic reaction is going to cool the solution because it's going to pull in energy from the solution to the system. So let's go through an example. We're going to calculate the change in enthalpy, which is the molar heat capacity. We're going to use molar heat capacity, so we're going to use the change in enthalpy looking at kilojoules per mole. When 500 milliliters of a 1 molar sodium hydroxide solution and 500 milliliters of a 1 molar hydrochloric acid solution react to form water. Both solutions are initially at 23.5 degrees Celsius, and a final solution reaches a temperature of 27.5 degrees Celsius. Because of the low concentrations of sodium hydroxide and hydrochloric acid, we're going to assume they behave similarly to water. This means that they have a specific heat of 4.18 joules per gram degree Celsius, and their density is 1 gram per milliliter. So my formula for my change in enthalpy of a reaction, or my delta H, is equal to mass times specific heat times change in temperature. Now I am told my volumes, I have 500 milliliters of one and 500 milliliters of the other, and because we're saying the density is pretty close to water, for every 1 milliliter it has a mass of 1 gram, so I can say that I have 1,000 grams of solution. I said my specific heat here we're going to assume is like water because of the low concentration, so my specific heat is 4.18 joules per gram degree Celsius. And my solutions are going from 23.5 to 27.5, so change in temperature is final minus initial. And this I'm measuring of my solution surrounding my reaction. Okay, so remember I'm measuring my surroundings. When I plug this in, I get 16,700 joules. But looking up, I need kilojoules. So divided by 1,000, I get 16.7 kilojoules. This energy came from an increase in temperature. Because of the increase in temperature, that came from my reaction to the surroundings. Because of this, it's exothermic, and my change here, my energy, my heat of reaction, needs to be negative. So because of this, I have to have a negative 16.7 kilojoules. Now I want to have my kilojoules per mole, so I need to divide my reaction by my moles of water. To do this, to figure out my moles, I need to do some stoichiometry. to figure out if either one of my two reactants is limiting in my amount of water that is made. So using my molarity, and knowing that in my reaction, everything is 1-to-1, I know that for every 1 mole of sodium hydroxide, I have 1 mole of water. Therefore, neither one of these is limiting. So I'm going to make 0.5 moles of water. After dividing those two, I get a total change in enthalpy of negative 33.4, so 33.4 kilojoules per mole. This means that heat flowed from my system to the surroundings. Right? My two reactants at the same temperature were mixed. My resulting solution went up in temperature, so the reaction taking place is exothermic, going from the system to the surroundings. So writing my equation, my hydrogen ions reacted with my trihydroxide ions to make water and released 33.4 kilojoules of heat energy. Therefore, I have an exothermic reaction.